behalf of everyone.
Thank you.
And now we are moving to next lecture. So I am very, very happy now to introduce Professor José María de Teresa from Universidad de Zaragoza and the Spanish Council of Research. This is the Institute of Material Science of Aragón. Then Professor José María de Teresa leads the group of nanofabrication and advanced microscopies at this Institute of Material Science. Besides, José María is the coordinator of the Spanish network on nanolithography and the focused ion beam area in the Spanish National Facility for Advanced Microscopies. He's a board member of the Condensed Matter Division in the European Physical Society. His main research interests are nanofabrication with focused electron and ion beams, magnetic nanostructures, nano superconductivity, and epitaxial graphene. He's got more than 200 research articles and 75 invited lecturers, plus one today that we will be so lucky to receive. And the title of his class today is Spin-Dependent Transport, Gmr and Tmr. Then do we have José María here?
Okay, hello, good afternoon.
Hi.
Can you see my screen?
Perfectly well.
Okay, so first I would like to thank Monse, Fernando, and the rest of the program committee to gather this very nice program, and also for the invitation to give this talk. In fact, I feel great responsibility because I have been sandwiched between two great speakers, Jairo and Felix, but I hope that you will enjoy my talk. So in the first slide, you can see, here I'm going to change this, okay, good. So in the first figure of the first slide, I have put a figure inside the Spintronics factory paper, in which you can see the great opportunities. Some of them are already existing, some of them are future applications in which Spintronics can play an important role. In my talk, I will discuss mainly giant magnetoresistance and tunnel magnetoresistance, which have applications in magnetic random access memories or in sensors such as magnetoresistive read heads or in position sensors, magnetic biosensors, but Gmr and Tmr permeate most of these applications. Okay, so when one starts to grow up, starts to ask himself some existential questions. Where do we come from? Where are we going? So here maybe you are a fresh student, you can ask yourself, okay, where is magnetism coming from in Spain? Then I found this very nice picture. This is Blas Cabrera. He's one of the pioneers in magnetism in Spain. So this picture was taken in 1932, and you can see very important scientists here, such as Bohr, Einstein, Langevin, Debye, and Blas Cabrera at that time was studying paramagnetic salts, and you can see that he was at similar level, let's say, discussing with very important scientists. So what is remarkable in this picture is who took this picture, because this picture was taken by Queen Elizabeth from Belgium. So you can imagine at that time, 100 years ago, so the important people were the scientists, and the queens and the kings were taking the picture of the scientists. Well, also I found this very nice picture taken 10 years ago, and we organized a small workshop in Santiago de Compostela that we named Spintronics Workshop. And then there we met some postdocs and collaborators of Albert Fert. You can see, you will recognize some faces and some names here. And it was a very inspiring small workshop. And okay, now we are living another historical date, because it's the first summer school, or the first school of Spintronics here in Spain. Okay, this is the outline of the talk. I have 4 main points and last remarks. So first, I will introduce spin-dependent transport phenomena. Then I will discuss more in detail giant magnetoresistance. In the following, tunnel magnetoresistance, and finally, some applications of Gmr and Tmr. Okay, I don't have good news for you. Spin-dependent transport is a very complex physical phenomenon. So there are many different physical aspects involved, and we should not be naive about spin-dependent electrical transport. So only some, for example, only some of magnetoresistive effects are caused by spin-dependent transport. So I have generated this blue medal. So when I discuss one of these spin-dependent transport phenomena, I will put this blue medal. But you will see that some other magnetoresistive effects are not caused by spin-dependent transport. But okay, for a few minutes, let me assume that the behavior of the electrical resistance under the magnetic field gives crucial information on the spin-dependent transport. Good, for the fresh students, maybe you have never measured electrical resistance. So how will I measure electrical resistance? You should have 4 electrical contacts. In the external ones, you make some current passed, and then you measure voltage by the inner contacts. Then you can calculate the resistance by the quotient of the current and the voltage. And you can calculate the resistivity. You use 4 electrical contacts because you can remove offset signals, and you can get rid of some thermoelectric effects, electromotive forces, etc. Good. Then there was one scientist 160 years ago, Lord Kelvin, which had the idea for the first time of measuring electrical resistance under application of magnetic field. And then he measured a change of resistance when he applied the magnetic field. So one can calculate the magnetoresistance as the difference between the resistance under magnetic field and the resistance at zero field divided by the resistance under zero field and multiplied by 100. Okay, so far so good. But then he had another crazy idea. He decided to measure the resistance of the sample, not only with the magnetic field perpendicular to the sample, but also parallel to the sample, parallel to the electrical current. So he did that on magnetic materials, ferromagnetic materials such as iron and nickel, and then he found a difference. So he discovered the anisotropic magnetoresistance effect. I put here the blue medal because this is spin-dependent transport phenomena. Okay, so we are talking about this here. We have current in this direction, and then we measure resistance with the magnetic field applied perpendicular or parallel to the current. Okay, then in a polycrystal, you can calculate the change of the resistance when you apply this field, this field parallel or perpendicular to the current. And then you can compare a zero magnetic induction. What is the difference between the resistance in for the perpendicular configuration or for the parallel configuration? And then you will see that you obtain a difference, and this is the anisotropic magnetoresistance. If you change continuously this theta angle between the magnetization and the current, in a polycrystal, you will find this dependence with the cosine, square cosine of this angle. So it was found experimentally that this anisotropic magnetoresistance can be either positive or negative. So what is the origin of this effect? So it's very complex phenomena, and the origin can change from one material to another, but there is one very important ingredient, which is the spin-orbit interaction effect. So we can intuitively explain this effect in the following way. If we have an spin-orbit interaction, then you have some orbital rearrangement when the magnetic field orders the spin of the material, and then you change the cross section of these orbitals for the conduction electron. So the conduction electron will see a different arrangement of the orbitals when the magnetization is parallel or is perpendicular to the current. Okay. So how was it demonstrated? There were some experiments in which there were magnetic impurities on gold, and then these impurities could have this orbital moment different from 0 or equal to 0. So when the dopant was holmium, where this orbital moment was different from 0, then there was a difference between the resistance with the field parallel or perpendicular to the current. But in gadolinium, where this orbital moment is 0, there was no difference. So this demonstrated that spin-orbit interaction is important in anisotropic magnetoresistance. Okay, this effect is normally small. So in some alloys, it can be a bit higher, such as in this nickel cobalt or nickel iron. It can go up to 6% at room temperature. And in fact, this effect was used in the first magnetoresistive briquettes, as we will see later. In some materials, it was shown that this anisotropic magnetoresistance could be expressed as the product of the spin orbit constant and alpha minus 1, where alpha is the quotient between the resistance for the spin up electrons divided by the spin down electrons. This is very important because this is a signature that spin-dependent transport is important in this phenomenon. However, as I mentioned, this phenomenon is complicated. For example, in single crystals, such as in these magnetite thin films, we find that the resistance is different in different crystallographic directions, and also the anisotropic magnetoresistance can even change the sign from one direction to another. So when you apply the electrical current through 100 direction, anisotropic magnetoresistance is positive, but if you apply it along the 110, it's negative. So as I mentioned, this is a spin-dependent transport phenomena, but is relatively small, and okay, the physical phenomena is a bit complicated. So in many cases, you find other classical magnetoresistance effects which are not produced by spin. And this is called Lorentz magnetoresistance, also called classical magnetoresistance, which is caused by the Lorentz force exerted on a moving charged particle under the influence of a magnetic field. And this effect is also responsible for the ordinary Hall effect. Okay, so if you apply a current to a material under the influence of a magnetic field, you have electrons and you have holes which go to different parts, and then you create a voltage. This is the Hall voltage. But in a material with a long mean-free path, what you can have is helical trajectories for the charges due to this Lorentz force, which is proportional to the velocity and to the magnetic field. So this magnetic field is delaying the path, the trajectory of the charge. So you are increasing the resistance. So this is a positive magnetoresistance effect. In general, this effect is small, but in some cases, such as in materials with long mean-free paths, like bismuth, it can be very high. For example, you can see at room temperature in this single crystal, one can observe magnetoresistance greater than 200%. And at low fields, it follows the square B dependence. Okay. So let's discuss about another effect, spin disorder magnetoresistance, which was also found in the surrounding of cool temperature of certain materials. Okay, it was found that in magnetic materials, at the Curie temperature, there was a decrease in the resistance. So this could be explained if there was an exchange interaction between the conduction electrons and the localized electrons. So the conduction electron feels a lower energy if its spin is aligned with the spin of the localized electron. Okay. So how will magnetic field affect this resistance? Yes, in the surrounding of TC, you can enhance the magnetization orientation in the direction of the magnetic field, and then you can decrease the resistance of the conduction electrons. Okay, so in many cases, you could explain the resistivity of your material applying this simple Mathiesen rule, in which resistivity was caused by defects, another term caused by phonons, and another term caused by magnetism. Okay, so to put it in simple words, if you apply the Drude's formula for a free electron material, then the resistivity is determined by the effective mass of the carrier, the density of these carriers, electrical charge, and the scattering time, with the scattering time being the quotient between the mean-free path and the Fermi velocity. The mean-free path is the path between two consecutive scattering events. So in a simplified view, which work in many cases, the inverse of the scattering time could have three different contributions: the contribution of defects, the contribution of phonons, and the contribution of the magnetic origin. Okay, so this seemed to work for many cases, but then in the 80s, everything changed when a new magnetoresistive effect appeared, which was called the giant magnetoresistance effect. So this is spin-dependent transport, and the first breakthrough idea came in the 30s. It was Neville Mott who suggested that in a ferromagnetic material, the spin of an electron can have an influence in its mobility. Okay, so the current is provided by the highly mobile S electrons, which suffer scattering with the mostly localized D electron. And this scattering can be spin dependent. So imagine you have a ferromagnetic material, you will have most of the localized spins in one direction, and only a few will have other direction. So for the conduction electron with the spin in the same direction, he will feel a lower potential. So he will be happy with having the spin direction in the same direction. And the scattering time will be 1 divided by the square of this interaction potential times the density of states at the Fermi level. So let's call this the resistivity of the spin-up channel. However, for the spin-down electrons, they will see a higher potential because the exchange interaction with the localized electrons will give an additional charge. So the resistivity of the spin-down channel will be different. So if we assume that in certain conditions, such as at low temperatures and with low mean-free paths, we have two conduction channels in parallel, the spin-up resistivity for the spin-up electrons and the spin-down resistivity for the spin-down electrons, then we can consider that the conductivity is given by these two parallel channels with this important property that the resistivity of the spin-down channel is different to that of the spin-up channel. So in this context, there is a new concept that we have to introduce, which is the spin diffusion length, which is the distance between two scattering events which produce a spin flip. So most of the scattering events will not produce the spin flip, but when it is produced, this distance is called the spin diffusion length. Okay, so we have the first ingredient, but no application from the 30s until the 80s. So in the 80s, there were new thin film growth machines, molecular beam epitaxis and sputtering machines that allow preparing materials with a very good control of the thickness, of the roughness. And then it was possible to grow multi-layers of ferromagnetic and non-magnetic materials with very clean interfaces. So if we are able to create one of these multi-layers in which we have materials with a spin diffusion lengths greater than the layer thickness, then we will observe a new phenomenon. This is the giant magnetoresistance. So for that, what one needs to compare is the resistance when we have an antiparallel magnetic configuration of the ferromagnetic layers with the resistance in the case of parallel alignment of the ferromagnetic magnetization of the ferromagnetic layers. So in a simple way, you can calculate the resistivity in this antiparallel configuration by taking into account what is the resistivity of the spin-up channel. In the spin-up channel, what you will see is that only in the ferromagnetic layers with antiparallel magnetization, he will suffer scattering. It's the same for the spin down electrons. In this case, only for the layers with magnetization in the other direction will suffer scattering. Okay, so you can calculate the value, total value of resistivity, and is this value. When you have all the ferromagnetic layers aligned in a parallel way, then for the spin up channel, there is very little scattering. So the current is mostly shunted through the layers. However, for the spin down electrons, then it will suffer scattering in all the ferromagnetic layers. So you can calculate the resistivity in this parallel configuration and you get this result. So if you calculate the difference, you obtain the giant magnetoresistance. And the important parameter here is the square of the difference between the resistivity of the spin down channel and the spin up channel. So if you are able to prepare these layers and to obtain this antiparallel configuration, you will obtain a giant magnetoresistance effect. But then we needed a third breakthrough idea. And the third idea was to be capable of achieving an antiparallel and a parallel magnetic configuration. The parallel magnetic configuration is very easy. You apply magnetic field and all the ferromagnetic layers will align in the direction of the field. But how to achieve at zero field this antiparallel magnetic configuration? Okay, so for that, we need the Rkky interaction. So this is an interaction which was known at that time between magnetic impurities in a metal. And depending on the distance between these impurities, it was observed that the exchange interaction, the sign of the exchange interaction was oscillating with the distance. So it has this dependence with this formula. And this is related to the Friedel charge oscillations of a magnetic impurity in a metal. Good. So can we do the same thing with the multilayers? Yes. So we see here one example with cobalt copper multilayers. So it was found when this magnetoresistance was tried to measure that for certain copper layers, they did not observe any magnetoresistance. It's because they could not achieve this antiparallel configuration between the ferromagnetic layers. But in other copper layer thicknesses, they were able to observe a large magnetoresistance because there was an anti-ferromagnetic coupling between the ferromagnetic layers due to this Rkky interaction. So they were in the right distance to observe this antiparallel configuration. Similarly, it was found in the iron chromium multilayers. Good. So now we have all the ingredients and then the results. We see here the results of Peter Grünberg's group, which was obtained in one trilayer with iron, chromium, and iron trilayer, and they observed at room temperature magnetoresistance of 1.5%. And then the group of Albert Fert in France, they did a multi-layer of these iron chromium stacks, and they were able to observe at 4.2 Kelvin magnetoresistance of 50%. So both results were obtained in 1988, and as Albert Fert mentioned in an interview, both showed the results in a conference in Lake Pesau, in the International Conference of Magnetic Field and Surfaces, and they realized that they both had found the same effect. And here, this is a blue metal, so it's a spin-dependent transport property, but also is a Nobel Prize medal. Good. So is the physics of this giant magnetoresistance as simple as I have mentioned? Okay, no, it's complicated. Just a couple of ideas here. First, you have to take into account that it's not the same to have a current in plane geometry in which the current goes mostly through the layers of the stack compared to current perpendicular to plane geometry. In this case, most of the time the current is crossing the interfaces between the different layers. And you can also have current forming an angle with the stack. The current perpendicular to plane geometry always gives higher magnetoresistance ratios compared to current in plane. Okay, what is the reason? The reason is that the electrons involved in the conduction and the exact physical processes taking place in the current in plane or current perpendicular to plane geometries are slightly different. So just here, a few ideas that okay, you can see in more detail in this chapter here. So this is what would happen for conduction electrons with a spin down or a spin up, for example, in the parallel configuration. So for the spin down channel, it will see on the ferromagnetic layers a high potential because the exchange interaction will make this high potential to appear. And also there are interface scattering potential. So at the interfaces, there are normally defects that will affect a lot the resistivity. And also in the inner part of the layers, you will have this called bulk scattering potentials. Now, if you take into account the potential seen by spin-up channel in the parallel configuration, in this case, the potential will be lower in the ferromagnetic layers and also for the magnetic impurities. And for the spin-up or spin-down channels in the antiparallel configuration, there will be an alternation between the potential in the ferromagnetic layers when they find the parallel or antiparallel ferromagnetic direction. Okay, good. Another point to highlight is that this simple, let's say, layer by layer approach is true if the mean free path is shorter than the layer thickness. But if the mean free path is very long, then there are reflections at the interfaces and there are interference between the wave functions. And then you have to apply a superlattice model, which is even more complicated. So I have given you a few ingredients of the theory, but we don't have time to discuss in detail all these very subtle effects. Okay, from the experimental perspective, we can also say that a similar effect can be obtained in a simpler material. In this case, a granular material. So you can prepare a granular material with ferromagnetic grains and with non-ferromagnetic metallic grains, such as this cobalt aluminum granular material. So at zero magnetic field, you will have magnetization, which is in principle randomly distributed. And when you apply the magnetic field, you have parallel alignment of the magnetization of the grains. So you will obtain something similar to the giant magnetoresistance effect we have observed in multi-layers. In fact, this is what one can observe as one magnetizes this granular material, one observes the decrease of the resistivity. Okay, this type of response is less suitable for applications, especially if there are some hysteresis. So in many cases at low temperatures, you observe hysteresis. Good. So now we change gears and we proceed to the next spin-dependent transport phenomena to discuss in detail, with this tunnel magnetoresistance. So the origin of this effect is very curious because as far as in 1975, Julier presented in one article that he had obtained a magnetoresistance effect in a structure with two ferromagnetic layers separated by a semiconductor that was acting as an insulating barrier. The effect was slightly higher than 10%, and it was a novel effect. And he was a PhD student, and he published this result as the only author of the paper. And the reason for that was that his PhD advisor was not convinced that this result was intrinsic, and he did not want to co-author the paper. And Julier finished his PhD thesis, and then he was working on other topics, and he only was called to a PhD defense 20 or 25 years later, and then he discovered that the result he had obtained and the phenomenon he had obtained in his PhD thesis was now a very, very large research topic in the world. He was surprised about that. Okay, this result was, some people tried to reproduce in other labs, and nobody achieved to reproduce this result using these materials. But a few years later, Maekawa and Geithberg, using nickel oxide insulating layer and cobalt, were able to measure some effect, which was not very good, just a few, was not very large, a few percent, but they interpreted it as due to this tunnel magnetoresistance that that Julier had proposed. A few years later, the group of Jagadish Mudera in MIT grew this in a very reproducible way, this cobalt iron, alumina cobalt trilayers, and then he was able to observe magnetoresistance greater than 10%, which was reproducible. And then the research on this topic started to explode. So what is the idea behind this effect? So you know that quantum mechanics allows some tunneling effect, which is a phenomenon that whose probability depends exponentially with the width of this insulating barrier. So if one tries to solve the Schrödinger equation of an incident wave, you will see that there is a certain transmission probability. And this, which is different from zero, so we can have tunneling of electrons from one side to the barrier to the other side. So you calculate the channel current, you will see that it depends on some transmission probability, and then an exponential dependence with the barrier width and with the square root of the barrier height. Okay, to try, yeah. So here we can see what we obtain in good magnetic tunnel junctions. We observe that in the parallel magnetic configuration, we have a low resistance. In the antiparallel magnetic configuration, we have a high resistance. How can we explain that? So in the model proposed by Julier already in 75, he proposed that this tunnel magnetoresistance was proportional to the spin polarization at the Fermi level of the two ferromagnets. The spin polarization is the difference between the spin up and spin down sublattices at the Fermi level. So for that, he just had to assume that in the parallel magnetic configuration, the electrons from the spin up subband tunnel to the available density of states in the spin up subband of the second electron. This is one current, and you have to add a second current, which is the current from the spin down subband to the available density of states of the spin down subband in the second electron. Okay. What about the antiparallel magnetic configuration? In the antiparallel magnetic configuration, for the electron tunneling with a certain spin direction, now the majority density of states becomes the spin down subband. So now the electrons from the spin up subband has to tunnel to the available density of states in the spin down subband of the second electron. And the second channel of conduction is electrons from the spin down subband to the spin up subband of the second electron. Okay, so by doing the calculation of the current in these two configurations, then you obtain that it can be expressed just by the available density of states and in the first electrode and the available density of states of the second electrode. And you can express it as a function of this spin polarization. So this difference between the density of states in the spin up and the spin down subbands. So if you have a material with a high spin polarization, you will observe a high tunneling magnetoresistance. This is the model of Julier that is based just on the spin conservation during tunneling. Good. But a few experiments, some experiments a few years later in which I participated, we discovered that this simple model was not enough to explain the results, because we observed that the insulating barrier was also playing a role. So we decided to study these two ferromagnetic electrodes, manganite and cobalt. Manganite because it was supposed to be a half metal, so spin polarization equal to 1, and cobalt because it could give a good thermal dependence, a good temperature dependence. And then we prepared these samples with different barriers, such as strontium titanate or aluminum. And then we observed a striking result that when you use this strontium titanate barrier, the tunneling magnetoresistance was inverse. So the resistance was lower in the anti-parallel configuration compared to the parallel configuration. But if we use another barrier, aluminum, we observe the normal effect in which the resistance is higher for the anti-parallel configuration. So how could we explain that? Manganite only had one type of electrons at the Fermi level with positive spin polarization. So the only explanation is that cobalt was changing the spin polarization. How was this possible? So this was possible if the d electrons, the electrons from the d band of cobalt were carrying out the tunneling and not the s electrons, because the s electrons are positively spin polarized, as had been demonstrated in standard junctions with alumina barriers, such as in this one. But with this insulating barrier here, with this interface between cobalt and strontium titanate, was favoring the channeling of d electrons, and the electrons have more density of states for the spin down subband. This could explain this inverse tunneling magnetoresistance. So there was an active role played by the barrier. Okay, good. And then there was another idea that consisted in preparing these magnetic tunnel junctions with a single crystal in a single crystal form or highly textured form. And the first samples were based on iron magnesium oxide and iron cobalt layers. So these materials could be grown in situ with a very high crystallinity and a very high texture. In principle, they were single crystals. Okay, and the first tunnel junctions based on these materials were prepared here in Spain. Was prepared in the Instituto of Microelectrónica of Madrid by Alfonso Cebollada and Carlos Martínez Cuqueta. And okay, at that time we were collaborating with the group of Albert Fert in Paris, and it was possible to pattern these samples and to measure a very high magnetoresistance effect. At 30 Kelvin, this effect was around 60%, and at room temperature, it was 27%. And by that time, 2001, there were some theoretical calculations which indicated that in this iron magnesium oxide iron system, it could be possible to observe very, very high magnetoresistance of the order of hundreds of percent. And then there were other groups with very good growth machines who also grew these samples. These were the groups of Parkin and the groups of Yuasa, and they observed a very, very large magnetoresistance effect. So from our point here, 27% at room temperature, they were able to achieve more than 200% magnetoresistance. And then the topic exploded, and people started to investigate tunnel junctions based on magnesium oxide insulating barriers. So what is the physical explanation for this very high magnetoresistance? So here we have a low resistance in the parallel configuration and a high resistance in the anti-parallel configuration. So now we have to take into account that the conduction takes place through several subbands that exist at the Fermi energy in this material, in iron. So there are bands with different symmetries. They are called delta 1, delta 2, delta 5. And the most efficient conduction channel corresponds to electrons arising from this delta 1 band or subband, which goes in the parallel configuration to the same band in the second electron. So this is very efficient conduction. This is why the resistance is low in the parallel configuration. But in the anti-parallel configuration for the spin down subband, this delta 1 band does not exist at the Fermi level. So this very efficient conduction channel does not exist in the anti-parallel configuration. So there are other conduction channels which are less efficient, and this gives rise to a very high resistance. So basically, to put it in a simple way, so now in these junctions, we have to take into account not only the spin conservation, but also the band symmetry conservation during tunneling. This was the difference that made these magnesium oxide single crystal junctions to give this very large magnetoresistance of several hundreds of percent. Similarly to the case of giant magnetoresistance, the same tunneling magnetoresistance effect can occur in granular materials. So some groups prepared granular films with ferromagnetic materials such as iron, cobalt, or nickel, and then insulating grains such as silicon oxide, alumina, and then in zero magnetic field, the magnetization is randomly distributed, and under application of magnetic field is parallel. So one finds a change in resistance between zero field and a magnetic saturation field of this granular material. Similar effect can occur in granular materials, in polycrystals, in which the boundaries of the grains are insulated. For example, we observed that in these double perovskites, these iron molybdenum double perovskites, which tend to form insulating grains, and then at zero field, the magnetization of the grains is randomly distributed, and then by application of field, you can align. And we observed at around 1 Tesla, magnetoresistance, which can be as high as 30%. Good. So now let's start the last part of my talk, which corresponds to the applications. I will focus in the applications of Gmr and Tmr in two fields, magnetic random access memories and in sensors. Good. So in the case of sensors, I'm going to discuss three different applications: magnetoresistive reed heads, position sensors, and magnetic biosensors. Regarding the magnetoresistive reed heads in hard drive disks, that is probably the most known application of Gmr and Tmr, we have seen a strong evolution of the technology with time. So the first magnetoresistive heads were introduced around 1991, and the technology was anisotropic magnetoresistance. The magnetic resistance effect was, as I mentioned before, just a few %, but it was enough in order to have or to read the information for the areal densities that were taking place at that time, which was around 0.1 gigabit per square inch. The first Gmr head was introduced in 1997, only 9 years after the basic discovery took place by the groups of Peter Grünberg and Albert Fert. And the advantage here was that the magnetic resistance effect was higher. Then there was another step in the technology in around 2003, in which the technology changed from bits with in-plane magnetization to bits with perpendicular magnetization. This is called perpendicular recording, and then the footprint of the bits could be smaller, and this was the reason to change from in-plane magnetization to out-of-plane magnetization. Then around 2007, TMR heads were introduced with a higher magnetic resistance than in the case of GMR. And from then, this is the technology that has been mostly used for these magnetic resistive read heads in hard drive disk. Nowadays, we are in areal densities around 1 terabit per square inch. Good. So as Jairo already mentioned, this technology is incredible. So now we have head to disk distance, which is of just a few nanometers, 6, 7 nanometers. So the magnetic resistive read head flies 6, 7 nanometers above the surface of the hard drive disk. And the bit length today is of the order of 10 nanometers. So this is a great evolution in just these 30 years that has produced this boost of the areal density in hard disks. Okay, so a few more words about this technology. It was already introduced by Jairo. We have a magnetic hard disk. So this is typically a cobalt alloy in which we can, you have tracks, bit tracks, and in these bit tracks, in the in-plane magnetization recording, we have bits when the magnetization is aligned to the right or to the left, and there are stray fields at the interface between the bits, which are detected by the Gmr read sensor. Okay, so these are the magnetic disks, and each bit is composed by just a few grains. So if nowadays the bit length is just 10 nanometers, you can imagine that we have just a few grains in each bit. But I want to mention two key concepts that help to develop this magnetoresistive sensing. Without them, probably the technology would have not been successful. The first one was the concept of the spin valve. If you remember, when I showed the results of Grünberg and Fert, these were layers with two configurations of different resistance, but in sensing, you need to have, or it's better if you have a sensor with a linear response at low field, and this linear response is as high as possible. This was obtained with the spin valve concept and the cross anisotropy concept. The first concept, which was proposed and developed by Bernard Bieny and Stuart Parkin in IBM, was the following that you probably are aware of, in which one of the ferromagnetic layers becomes spin by the presence of an antiferromagnet. So due to the exchange bias interaction at the interface between the antiferromagnet and the antiferromagnet, you block the magnetization direction of the hard magnetic layer. And then you have the spacer, the non-magnetic spacer, and you have the free magnetic layer. So this material is chosen to have a low coercive field, so that when you measure magnetization as a function of field, you pass from a parallel magnetic configuration to an anti-parallel magnetic configuration at low field, and you would have to apply a very high field in order to overcome this exchange bias field here. So you are in this magnetoresistive grid head sensors working in these low fields here, where you will obtain all the magnetoresistance response. Okay, but in order to have this linear response at zero field, you need to introduce this crossed anisotropy. So the free layer is grown with easy magnetization direction perpendicular to the hard magnetic layer. So when you apply the magnetic field, this magnetic field is created by the stray fields from the magnetic beads. Then you rotate the magnetization of this free layer, and you rotate it in a continuous way, so that you obtain a change of resistance at low fields, which is linear. Okay, and this is what is used in for sensing with great efficacy. Good. So where are we today in this technology? So as I mentioned, the perpendicular magnetic recording was introduced a few years ago, and as Jairo already mentioned, we have this kind of technology with the reed heads, which are brought very close to the magnetic disk, and the sensor is just at the tip of this head, and with incredible small distances, we have the magnetic disk, which is has an overcoat of 3 nanometer, lubricant 1 nanometer, fly height only 5 nanometers, overcoat 2 nanometers, and then the magnetoresistive sensor. And this is a top-down image of the reed head on top of the track, of the bit track. So the bit length is as small as this one, is, as I mentioned, 10 nanometers or less nowadays. So it just contains a few grains of the magnetic material. And then you have here the magnetic tunnel junction. The magnetic tunnel junction, which is composed of the free layer, and then the tunnel barrier, and the second ferromagnetic layer. This is pinned, the magnetization of this layer is pinned by an antiferromagnet. It's not a simple antiferromagnet, is a synthetic antiferromagnet that I think it will be explained in another talk. I don't have time to explain it now. But you see also that the anisotropies, cross anisotropies, which will give rise to this linear response at low field. So we displace this reed head on the track, and then we read the information by moving the magnetization direction of the free layer and obtaining a change in the resistance of the head. So this is the technology nowadays. Okay, now we move to another sensing application of Gmr and Tmr, which is position sensors. Nowadays, it's common to find in our cell phones 3D magnetometers and digital compasses in our smartphones. Another important market is in automotive sensor, in automotive sector, because there we have many Gmr and Tmr sensors for detection, angular detection, speed detection, current detection, position switch sensors. So this can be used, for example, in anti-blocking system for braking our cars, or in order to have full control of the gear positions. Also in modern industry, there are some applications such as in current and power sensors, encoders and scanners. So this already exists and is a large market. Then the third sensing application I want to discuss is biosensors. So maybe I can quote what Peter Grünberg said in an interview just after he received the Nobel Prize. He said, "Since we are discussing on applications of Gmr for magnetic hard disks for many years, I'm not so excited anymore about this. But I found other applications where the giant magnetoresistance comes nicely very in. and that is for the detection of genetic material. So he was thinking about biosensors. In biosensors, you want to detect in a quantitative way an analyte. This analyte can be a hormone, an antigen, a virus, DNA strain. Okay, so one strategy is to functionalize a magnetic nanoparticle with some chemical molecule that can attach to the analyte. So if we have a substrate with an analyte bioconjugate, so some entity that is able to recognize from the biological point of view the analyte, then it will become blocked on this position. So for that, we can use antibodies, DNA, the complementary DNA strains, etc. So then we have the analyte, which becomes labeled, marked with a magnetic nanoparticle. So if we bring a magnetoresistive sensor in proximity of these nanoparticles, we will be able to detect the amount of magnetic nanoparticles. Then we can infer the quantity of analyte. So in fact, this was already tested in the 90s in naval research lab, such as in this publication here. So they use Gmr sensors with some functionalization in order to recognize certain warfare agents which were labeled with magnetic nanoparticles. They tested different warfare agents, and they were able to find changes in the magnetoresistive sensor resistance. So they were able to use it for biosensing. I can mention one example in which we were working for a few years, which were lateral flow tests, like the ones that are used for pregnancy test and other many tests that are used, such as COVID virus, etc. So basically here you have in this lateral flow stripes, you have a capture antibody that will recognize the analyte you want to detect. And you have labeled this analyte with magnetic nanoparticles. So if this analyte is in a solution, when it flows, this solution flows through the lateral flow stripe, then it will become blocked at the position of the capture antibody. So now the point is how to bring the magnetoresistive sensor in proximity to these particles. So at that time, a few years ago, we designed this sensing scheme in which we had a Gmr sensor. These were produced by a group of Paulo Freitas in ESC. And then the stripe was glued to a wheel that was scanned on top of the Gmr sensor. And then when our analyte, our targeted analyte, which in our case was HCG hormone, was on the stripe, then as it was marked with the magnetic nanoparticles, we observed a change in the sensor resistance. And we could do quantitative measurements of the change in the sensor resistance as a function of the hormone concentration. I call your attention to a recent review article on sensing in which they discuss in detail these magnetic biosensors. Okay, and the last application of Gmr and Tmr is for MRAMs. It was already introduced by Jairo Sinova. So nowadays, these spin transfer torque MRAMs have been very successful, as you will see in the next slides. So the basic idea was already proposed in the 90s. So you have these Gmr or Tmr stacks with two different configurations, anti-parallel and parallel, which will give rise to different resistance state. And then you need some accessing lines and word lines, bit lines that in the first design you could use to measure, to put current in this stack and to measure the resistance. And also you could inject current in order to create stray fields that would change the magnetization direction of the free layer, and then you could write on these stacks. Okay, so this was the first strategy, in which, of course, you have to combine with a transistor in order to select individually each of these units of memory. So this is possible. Here you have one transmission electron microscopy image of this kind of technology, in which first in the front end of line, you can grow the CMOS transistor, and then on another layer, you can grow the MRAM sensors, and then you can select through this transistor the unique unit of memory that you want to address by using these bit lines and word lines, etc. This is also called toggle MRAM. But in the last years, a more interesting scheme has been developed, which is the spin transfer torque MRAM concept. In this case, we don't need to produce stray fields. It's the application of a high electrical current that is able to apply a spin transfer torque in order to write in the memory. So you are able to change the magnetization direction of the free layer, and then you are able to write, and of course you are able to read by reading the resistance of the stack. These STT MRAMs can be designed with in-plane magnetization direction or out-of-plane magnetization direction. Both schemes have been tested positively. And also it's interesting, another concept that has been proposed is a bit delayed in time, but it seems it's coming, which is the spin orbit transfer torque MRAM. So here, the idea is that it's better not to pass current to write on the tunnel junction, because if you pass current many times and a high current, you can deteriorate, you can damage the junction. But if you have a material in which you can create a high spin current by passing current through it, and there are some physical phenomena we will see these days that in this course that can produce these spin currents, this spin current can be enough to change the magnetization direction of the free layer. So this is called the SOT MRAM. So what is the advantage of STT MRAM compared to standard semiconductor dynamic RAM? So there are some advantages. They are radiation hard. You need less power. You have more better temperature tolerance. You have similar storage capacity. The access speed is still not as good as in DRAM, but is becoming closer, and the endurance is similar. So I want to highlight this point of power. So nowadays, as you know, power consumption is one of the main problems of electronics. And here we can compare the energy consumption by memory semiconductor type for the programming of 1 bit. So in DRAM or SRAM, you need an energy of 120 picojoules. Flash memories, 5 picojoules. In a standard MRAMs, such as in this one, the toggle MRAM, between 30 and 120 picojoules. But in STT MRAM, it's as low as 0.4 picojoules. So this is why companies have put a lot of effort in the fabrication of these STT RAMs. And okay, yesterday I was having a look on the latest developments of these MRAMs in industry. You can follow on this webpage these developments. And I have seen that in August last year, EverSpin, the company EverSpin, started production of 1 gigabit STT MRAMs. And in December last year and February this year, IBM and Samsung announced that they are fabricated and embedded MRAMs. So they are embedded in the conventional CMOS semiconductor technology. And okay, they are already in very advanced nodes, in 14 nanometer node and in 28 nanometer node. And switching speed of 3 nanoseconds have been announced. So this is really a very promising, it's already a reality in today's technology. And the company Samsung has announced that they plan to apply these STT MRAMs in automotive, wearable, graphic memory, low-level cache, Internet of Things, and edge artificial intelligence markets. And also another application, which is more niche, but is also being fabricated by Avalanche Technology, is the production of memories for space. As you know, semiconductors cannot be used in space because they are not radiation hard, but these MRAMs, which are mainly based on metallic materials, they stand much better space radiation. So even if the memories are lower because you cannot use semiconductors, they are enough for these space applications. So I have 2 slides for the last remarks. So I would say that there are some challenges for Gmr and Tmr, and this is good because researchers can still be working on these topics. I will mention a few of them. It's important for these applications to obtain higher signal-to-noise ratios, and for that, normally what is important is to decrease the resistance of the devices themselves, because the white noise is proportional to the resistance of the device. So the lower the resistance of the devices, the better. So for that, we want to approach this area here. So here in this axis here, we have magnetic resistance, and here we have the resistance. So we want to have a very high magnetic resistance of the devices with low resistance of the devices. Also, there are some challenges regarding scaling. We want to do really very, very small devices, and nanolithography is not so simple when you approach these very small dimensions below 10 nanometers. We want to have higher sensitivity, and for that, there are some new materials that have been studied, such as Hoysled alloys or the 2D material that have been mentioned. And there are also some interesting problems related to the engineering of the interfaces that can improve this sensitivity. Okay, in the case of the STT MRAMs, it would be important to lower the switching currents. Also for the production, at the end of the day, the devices have to be fabricated at the wafer scale on 300 millimeter wafers. So you need to be able to produce all these materials with homogeneity at that level, 300 millimeter, which is not simple. This is a filter for the use of many materials. And also you need to have testing tools for these very small devices. So there is a lot of paths to work on. Okay, I have seen also that there are recent developments that can be interesting. So apart of STT and SOT MRAMs, we have voltage control magnetic anisotropy. So if instead of needing to apply current, we only need to apply voltage without passing current, and we are able to change the magnetization direction of the free layer, this would still lower the power consumption. That would be good. And there are, of course, new schemes such as memories based on domain walls, skirmions, etc., that are being investigated. So I see a future which is very bright for Gmr and Tmr. And then my last slide. So when Fernando proposed me to prepare this talk, I thought this would be very difficult because this song here, Welcome to the Jungle, came to my mind because the magnetic resistance scenario is really a jungle. So for a few years, I was working in this topic, and every year there was a new magnetic resistive effect which came in. And it was difficult to keep pace with all these magnetic resistant effects. I can imagine now for a fresh student landing in this topic of magnetic resistance, and then suddenly they see all these magnetic resistance effects. The ones I mentioned today, anisotropy magnetic resistance, tunnel magnetic resistance, giant magnetic resistance, Lorentz magnetic resistance, spin disorder magnetic resistance, and many others that I did not talk about but are very interesting. Colossal magnetic resistance, domain wall magnetic resistance, extraordinary magnetic resistance, ballistic magnetic resistance, Rasba LST magnetic resistance, spin hole magnetic resistance. So I guess that it can be overwhelming, but I try to focus on the most interesting four applications, which are Gmr and Tmr. And I hope that at least on these two topics, you have taken the flavor of what's going on and the applications nowadays and the future. And as was mentioned by Monse, nowadays I'm coordinator of the Spanish network on nanolithography. This is a broader network of this Spintronics network. And okay, I want to announce that we have a summer school in around 1 month. So you can still register for that. So you have a web page here, and also in the web page of University of Salamanca, who is organizing this summer school, and this can be on site. You can attend on site or online. So you have both options if you want to travel or you don't want to travel. And also in our network, we have just opened the call for a prize for PhD thesis which are using nanolithography. So this is all I wanted to say. Maybe I was a bit long, but I hope you have enjoyed the talk, and thank you very much for your attention.
Thank you, Jose Maria, for guiding us through this magnetoresistance jungle. Thank you for the incredibly instructive and enlightening lecture. We give you the gold medal, I think.
Thank you.
It is really very challenging to explain this. There are a lot of subtle details and a lot of knowledge behind this, and that is so interesting. Thank you very much. Well, I think that we have a few questions. I had my own question, because if the Queen of Belgium took the first photo in your presentation, who took the second one? Maybe the King of Spain?
Sorry.
Okay. Yeah, here I find now the questions from the chat. And we have already 3 questions. Look, first question is by Julián Zúñiga from Colombia. Mm-hmm. And he is asking for a TMR spin valve with CIP. If one applies an electric field in the insulating material, the semiconductor, perpendicular to the growth plane, when the magnetic fields are parallel, the resistance decreases more than if it were not done. So if one applies an electric field in the insulating material perpendicular to the growth plane.
In TMR, you mean in TMR?
Yeah, TMR with CIP, TMR spin valve.
Yeah, with, okay. So, yeah, I think a few years ago in the 90s, there were some tries to grow these edge junctions, but I think the reproducibility was not very good. I don't know if this is the question. I'm not familiar with this geometry. I think it's not very conventional. If I understood correctly the question, which I cannot see in written.
Okay, I will paste it for you. Maybe I will paste it for you in the chat, and maybe you can tell us later in our chat, I mean, because you don't have access. Okay, I will paste it here. Okay. I think you've got it.
Okay.
Maybe this will help.
Okay.
I think it says, does the resistance decreases more than if we did not apply an electric field perpendicular to the insulating film?
So for me, the concept of TMR in CIP is not a standard, so I don't understand the.
Yeah, maybe too challenging a question. Then, of course, one cannot have everything, every answer. But it seemed you had. Okay, let me ask you another question by Vitor Alexandre, who thanks you for the nice class. And can you talk a little about the colossal magnetic resistance? I think you just mentioned. Still, he says something else, if you don't mind.
Yes.
I know this phenomenon exists in oxides as lanthanum, strontium, manganese, LSMO, but I don't know how much about it. Thank a lot for commenting.
Yeah, this could be another talk. Yeah, so this was studied mainly in the 90s. And yeah, so there you had materials with phase separation. and you have in the sample part of the material which was conducting and part of the material which was insulating. And as a result of that, the overall behavior was a high resistance. But then when application of magnetic field, then the metallic ferromagnetic phase expanded at the cost of the insulating phase. And then the material became conducting. So there was a change in resistance of several orders of magnitude. And this is the reason why it was called colossal magnetoresistance. But the problem with this type of magnetoresistive effect was that the applied magnetic field you needed was very high, typically in the range of a few Teslas. And the response was not linear with the magnetic field. So finally, it did not find application in industry because Gmr and Tmr were more effective. But the physics behind colossal magnetoresistance was really very interesting. You had the formation of magnetic polarons. Recently, last year, Steve Follmornar died, who was one of the persons who introduced magnetic polarons in condensed matter physics. And this concept was also crucial in colossal magnetoresistance because you had this phase segregation with these magnetic polarons with ferromagnetic interaction by double exchange, and then the insulating part of the material, and with applied magnetic field, you expanded the ferromagnetic conductive part. So it's interesting physics, but not for applications.
Okay, clear. Thank you. I still have another question by José Solano, who asks, thanks for the very well condensed talk. I have two questions, so I will put the first question first. He asks, what produces the change of band structure between the parallel and the anti-parallel configurations in the magnesium oxide system? That's the first question. What produces the change of band structure? Well, we have very specific questions, I think.
Yes. So I guess it's about the inverse tunnel magnetoresistance. It's about this this result. Here is this. What he's asking.
Yeah, I put the question in our chat for you. What produces the change of band structure? Between the parallel and anti-parallel.
In the iron magnesium oxide. Okay, okay. Sorry.
Our magnesium oxide system.
Yeah, so you have the exchange interaction, and then you have the spin up and the spin down subbands, and then so the bottom part of the bands are very close to the Fermi level. So with this exchange splitting, you can shift it above the Fermi level in the spin down subband due to the exchange interaction. So this is the reason why this band disappears from the Fermi level, so the electrons cannot tunnel to that band.
Great, great. Now the other question was, what are the possible difficulties with the voltage modified magnetic anisotropy devices? Yeah,
so nowadays the problem, as far as I understood, is that it's not an efficient process, that you cannot rotate the magnetization very efficiently in the existing materials nowadays, and with the type, with the voltage amplitude that you want to apply. But I'm sure that this topic is going to be developed in the coming years. There are new materials coming in, new strategies. So I think this can be very promising to have lower power consumption. So yeah, I see future for that.
Okay, thank you very much, José María.